The student does an investigation to determine the number of waters of crystallization in a sample of hydrated sodium carbonate. So I'm going to find X here. The student dissolved 375 milligrams, so that's 0.375 grams of sodium carbonate in distilled water and made the solution up to 250 centimetres cubed in a volumetric flask. Right, let's draw a little picture here. So 250 centimetres cubed, and in there I've got 0.375 grams. So 0.375 grams of the carbonate. So let's read on. A pipette was used to add 25 centimetres cubed of this solution to a conical flask. So from here, 25 centimetres cubed, so that's a tenth. So if I go back the other way, I need to times it by 10. And this was titrated with 0.01 mole hydrochloric acid. So HCl concentration is 0.01. And what I need to do here is use these results to get the mean titer and go from there. Right, so mean titer, never use the rough result. So the two closest are these two here. So 26.55 and 26.65, which means my mean titer is 26.55 plus 26.65 divided by 2, which equals 26.60 centimetres cubed. So my volume here is 26.6 times 10 to the minus 3. So let's just look at the root. Okay, so the root that I need to do here now to get the waters of crystallization, I need the MR here, which is going to be the mass which I've got in the question divided by the number of moles. So I've got to get the number of moles of sodium carbonate. So I can get the number of moles here. It's a 1-to-1 ratio. It is not a 1-to-1 ratio. It is a 2-to-1 ratio. Okay, so to go from here to get the number of moles here, I need to divide that by 2. Okay, and then to get the number of moles here, I need to times it by 10. And that number of moles there goes into this bit here. So that's the root for the calculation. So let's start this off then. So number of moles of HCl is equal to concentration 0.01 times the volume 26.6 times 10 to the minus 3, and that gives me 2.66 times 10 to the minus 4, so that's that bit there. So to get my number of moles of sodium carbonate, 2CO3, now this is in the 25 centimetres cubed. That's going to be 2.66 times 10 to the minus 4 divided by 2, which is 1.33 times 10 to the minus 4. And then I need my number of moles of sodium carbonate in 250 centimetres cubed. So that's 1.33 times 10 to the minus 4 times 10, which is 1.33 times 10 to the minus 3. So I've now got this, I've got that in the question. So the MR is 0.375 divided by 1.33 times 10 to the minus 3, which equals 280 to three significant figures. Let's say that's 282. Okay, so in my crystal then, let's move this up a little bit, 2CO3.XH2O. So the MR of all of that is 282. The MR of this bit here is 106. So if I take those away, so 282 minus 106 gives you 176. So this bit here is 176. 176 divided by 18, that's the MR of water, gives me 10 to the nearest whole number. Remember, waters of crystallization have to be to the nearest whole number. So where are the marks? There's 1 mark for working out the mean titer, 1 mark for working out the moles of hydrochloric acid, 1 mark for working out the moles in 25, 1 mark for working out the moles in 250, 1 mark for the MR, and then 1 mark for this part here. Okay, let's move on. So B, the uncertainty in the pipette in this experiment is 0.06. Calculate the percentage uncertainty. So 0.06 divided by, and we took 25 out with the pipette, so times 100, and that equals 0.24%. The student rinses the burette with distilled water before filling the hydrochloric acid solution. State and explain the effect it would have on the value of the titer. So let's just go back to this bit here. So if I've rinsed this with water, there will be drops of water still in there when I fill it up with my hydrochloric acid, which means my hydrochloric acid will be dilute. So because it is more dilute than the 0.01 that we think it is, the volume that you would need to add to get the same number of moles to neutralise the sodium carbonate would be greater. So state and explain the effect. So the HCl be diluted, therefore greater volume in the titer would be required. And then part D, during the titration, the student washed the inside of the conical flask with some distilled water. Suggest why the washing does not give an incorrect result. Again, let's go back to this. So while you're doing a titration here, what you often get are little splashes that go up the side. And if you rinse that back in with a little bit of water, well, the water's not going to change anything. It doesn't react with the sodium carbonate. All it's going to do is wash any unreacted sodium carbonate back into the flask. So the number of moles that's in the flask hasn't changed. So it actually makes the whole process a little bit more accurate. So adding water doesn't change. The number of moles of the sodium carbonate.